Alright, so welcome back to another video. So in today's video, we're going to be dealing with the integral from 0 to 1 of the fractional of -1 to the power floor of 1 over x divided by x dx. So a fractional, and inside that fractional contains a floor function including. So it's also there's also a -1 based in the numerator divided by x in the denominator. So that should be a challenge. Obviously, I think the first thing I would want to do is we're going to do a u substitution. So we'll let u equals 1 over x, okay? And then since we got to plug in some terms for x, substitute x in terms of u. So how about I get x by itself? So in other words, this will have to mean that I'll just multiply x on both sides and divide u, so that I'll get x is equal to 1 divided by u. And so when I take its derivative both sides, so we get that dx is equal to, let's see, so this is -1 divided by u squared du. Okay, so now that we have that, so now we just rewrite our new integral. So we have to change our bounds. So let's see, so when x is equal to 0, so that means u would have to go to infinity, approach infinity, and then when x is equal to 1, so u would have to equal 1, and then we just plug in our, the inside of our fractional. So let's see, if I plug x for 1 over u, so this is division with 1 over u, so I'll just flip the reciprocal, so that means u will be in in the numerator. And then we're left with -1, and then to the power the floor of 1 over x, which we say that's u, so this will be the floor of u. And then we'll substitute our dx differential, so that's negative, so that'll be a negative over here, and then divided by u squared du. Okay, good. So now next is, notice that obviously we need to switch our bounds because we have that infinity is the bigger number, which acts as the lower bound, and then 1 is the smaller number, which acts as the upper bound. So that means we just change our bounds of integration. So it's infinity 1, so there's a negative, but then there's also a negative inside our as part of our integrand. So that means those negatives will cancel each other out. So we're left with now it's all positive u squared du. Okay, over here for u that's in the interval from n to n plus 1 open, then we can come to the conclusion that the floor of u is going to just equal n. So with that established, I can just substitute u for the floor of u for just n. So other words, rewrite this as 1 infinity, and then the fractional of -1 to the power n, and divided by u squared, and then multiply and du. Okay, so with that, and now now I want to rewrite our integral so that in a form of a sum. So we're a sum of integrals evaluated at each partition of our bounds. So we start from 1, and then we go to 2, and then 2 to 3, 2 to 3, then 3 to 4, then 4 to 5, and so on, so all the way up to infinity. So we have that this is our infinite sum, n is equal to 1 of the integral from n to n plus 1, and then the fractional -1n. I'm just moving the u to this side just so the constant, it goes to the front, and then divided by u squared du. So now let's pay attention to this. So because there's the base -1 to the power u, so no matter for which index you use for n is equal to 1, 2, and so forth, you're gonna get that this alternates. So when you plug n is equal to 1, you're gonna get that -1 to the power 1 is -1, and then you plug 2, you're gonna get that it's equal to +1. You plug n for equals 3, you're gonna get -1, so on and so forth. It alternates. The series alternates. So what we have to do now is, really what I can do is that I can actually split this integral into two different sums. it's really one sum that takes account of the odd ends, and then add that with this other sum that takes account of the even ends. So, and also that means that we're running the sum. So our first sum, we're taking account of the odd ends. So that means the lower bound really will have to be changed to an odd number. So this is 2n minus 1 and then 2n of okay, so it's the odd, so that means every odd end you plug in, you're gonna get a negative, so that means this is gonna be the fractional of negative u, and then divided by u squared, and then we add that with our other sum that takes account of the even ends, so n is equal 1 of 2n, that's our even, and then 2n plus 1, so we're doing increments of each one, and because we're dealing with, so even, so that becomes a positive, so we're just left with the fractional of just positive u, and then u squared du. Now let's actually recall that my eraser, it's fine. So let's recall that so fact that the fractional of u is actually just equal to u minus the floor of u. So we'll use that later. But also because we have that there's a fractional negative u, another definition of the fractional that we're going to be using is that the fractional negative u is actually just equal to 1 minus the fractional of u. And in other words, that also can be written as 1 minus u and then plus the floor of u. Okay, nice. So we use that definition to substitute our above sum. So now we can rewrite this as the following. So we get that the sum is, so infinite sum n is equal to 1. The same bounds from let's see, 2n minus 1 to 2n. Let's see, so this is 1 minus the fractional of u, and then u squared du, and then add that with our other sum, which takes account of the evens. So n is equal to 1, and then goes from 2n to 2n plus 1 of so where is it? The fractional of u is so we said this is u, but also because let's see, we're dealing with the fractional of u. So that means within the interval 2n to 2n plus 1, we have to plug that the floor of u is 2n. So this will be u minus 2n divided by u squared du. Now just rewriting the sum again, because now we have a factorial here, so I'll just substitute that a second time. N is equal to 1, so this is, let's see, 2n minus 1 and then 2n of 1 minus u, and then plus, so we're dealing with our intervals between 2n minus 1 to 2n, so if we take account of the floor, so we have to plug in that it the floor of u will have to be 2n minus 1. Okay, and then divided by u squared du. But then I can just substitute that. I can just rewrite this, and that's just only focusing on this term. I'll write the other sum in a sec. So let's see, 1 plus, so 1 minus negative 1. 1 plus negative 1 is 0. And then let's see, so it's 2n minus u, and then divided by u squared. Or hold on one sec, there's supposed to be an integral. And then we just add this to our, we add our other sum. So this one's from 2n and then 2n plus 1 of u minus 2n divided by u squared du. Okay, so now let's calculate our each of our intervals. Oops. So now let me first calculate this interval over here. So I'll just mark this. Well, I'll just write this in red. So let's see. The integral from 2n to 2n plus 1 of u minus 2n divided by u squared du. I can write this as two sums due to the fraction, so because of the numerator and they share the same denominator. So this means this is just 1 over u du, and then minus, so same thing, 2n plus 1, 2n, and then this is 2n u squared. Okay, but it's easy to solve the definite integrals for both of these. This is going to be ln of u evaluated from 2n plus 1 to 2n, and then subtract that with, so let's see, 2n is just a constant in this in our world of u, so I can just factor this outside, so we're left with 1 over u squared. Okay, so 1 over u squared when you take its antiderivative, so let's see, u to the negative 2, so plus 1, negative 1 divided by that, so negative 1, so this is just, that minus will come out, so this will be a plus, and then this will be, it'll just be 2n divided by u, and then from 2n plus 1 to 2n. Okay, and then, let's see, we'll get that this is ln of 2n plus 1 minus ln of 2n, okay, and then plus, so 2n divided by 2n plus 1 minus 2n divided by 2n, which is just 1. I can simply solve this even simplify this even further. So let's see, we can combine, let's see, these are subtractions of 2 natural logs, so I can actually just use our rules to combine this under 1 log, but that's under division, so then this will be 2n of 2n plus 1 divided by 2n, okay, and then plus, okay, so let's see, let's actually get a common denominator here, so this is 2n plus 1, and then that's minus 2n plus 1, so this should be a 2n plus 1 here, and then a 2n. Okay, so if we subtract these, we get 2n minus 2n is 0, then this is just negative 1, 2n plus 1. So therefore, this means this is 2n plus 1 divided by 2n, and then minus 1 divided by 2n plus 1. Okay, let me box this. Or rather, let me just underline this. This is our answer for this integral. Now we just have to solve this integral. But that's not actually difficult to show, because notice that this is just the same thing as before, but the numerator's just is commutative, so it changes. So this is 2n minus u, so it's different, but not only that, we also, our bounds are different that we need to evaluate as well. So, okay, let's do that. So now we just have to calculate this integral over here. So this is, let's see, 2n and then 2n minus 1 of 2n minus u divided by u squared du. Okay. Now that's also the same thing. I can just, by using linearity, I can just divide this and split this up into 2 integrals, the sum of 2 integrals, even though because they share the same denominator, so we can split that up. So this is 2n divided by u squared du, and then subtract that with 2n minus 1. Let's see, so it's minus u divided by u squared, so that's just 1 over u du. Okay, and then let's just go back to here. It's the same thing. So let's see, this is, so over here, this will be 2n divided by u, or negative specifically. So this is negative, so then this will be 2n, and then subtract that with our 1 over u antiderivative, so it's ln of u, and then with our bounds 2n and then 2n minus 1. Okay, cool. So when I evaluate it at our terms, so we get this is negative 2n divided by 2n, so that's negative 1, and then subtract that, well, this will be a plus, really, so then this will be 2n divided by 2n minus 1, okay, and then subtract that with our ln of 2n, and then plus, so minus, and then ln of 2n, and then minus ln of 2n minus 1. Okay. So let's fix this a bit. So let's see, let's get a common denominator. So this is, let's see, so 2n minus 1 and plus 2n minus 1. So that's 2n over here. So that's 2n minus 1 here, negative. Okay, and then minus, we use our rules of natural logs, so then this is simply just the same thing as the natural log of 2n divided by 2n minus 1. Okay, and then if we simplify this out, then let's see, negative 2n plus 2n cancels, and then I'll distribute the negative 1, so then this will be 1 divided by 2n minus 1, and then minus ln of 2n divided by 2n minus 1. Okay, cool. So we solve our two integrals, or yeah, the two integrals from here. So let's see, this is here. Here, I'll put it this way. So let me draw my little arrow. So this corresponds with this, and then the other one corresponds with this. So now we just fill in the pieces back. So let me just reiterate what we have. I just want to give myself just a little bit of room. Okay, reiterate what we have. So the sum u minus 2n divided by u squared du. And then simply this is just, let's say 2n minus 1. So this is from here. So then this is 2n minus 1 and minus ln of 2n divided by 2n minus 1. And then we add this with our other sum, which is ln of 2n divided by 2n plus 1. And then subtract that with 1 divided by 2n plus 1. Okay, so next what I'll do is that I'll just group these terms together, since this is commutative under addition. But not only that, they fall under the same index with this series. This is totally fine. So then I'll group the natural logs with each other. So then this will be, let's see, I'll put this term first, since this is the leading coefficient is its addition. So this is ln of 2n plus 1 divided by 2n, and then subtract that with ln of 2n divided by 2n minus 1. And then I'll just add this with our term. Let's see, the sum n is equal to 1. So let's see, this is 1 over 2n minus 1. And then subtract this with 1 divided by 2n plus 1. So how about first, let's focus on this series first. Okay, so let me mark this in red, or write this in red. Okay, so the series defined as follows. So 1 over 2n minus 1 minus 1 divided by 2n plus 1. Okay, so now let's actually expand this series out. So over here we get that, let's see, if I start at n is equal to 1, so I get that this is what? 1 divided by 2 times 1 minus 1, so that's 1. And then subtract that with, let's see, 1 over 2, 1 plus 1, so that's 1 over 3. Okay, then plus, next is n is equal to 2, so let's see, 4 is 3, so 1 over 3. And then over here, this will be 1 over 5, 1 over 7. Okay, so we just keep going all the way up to n, and we'll just take the limit as n approaches infinity. So let's see, this is 1 divided by 2n minus 1, and then minus 1 divided by 2n plus 1. As you can see here, we got these terms canceling. So negative 1/3 plus 1/3, 0, negative 1/4 plus 1/5, or 1/5. Yeah, that's 0. So they cancel. Negative 1/7, so on, they cancel, so on, so on, so forth, and then it cancels here. So we're actually just left with these two terms here, 1 and then plus negative 1 over 2n plus 1. But if we take this, the limit as n approaches infinity, so this is actually just going to converge to 0. So let me mark this up. So that this is cancels, 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 all the way so forth, this cancels. And then over here, this is just going to equal 0. So therefore, this series actually is just going to equal to just 1. 1 over 2n minus 1, then minus 1 divided by 2n plus 1 is just going to equal 1. And now the last thing we need to do is to evaluate our ln of the natural log. So over here, so this means right here, and then minus ln of 2n divided by 2n minus 1. So I can actually just, using our rules of natural logs, I can just combine this under one natural log. So let's see, this n is equal to 1. And then this is the natural log of, let's see, so this is 2n plus 1 divided by 2n. And then divide this with 2n divided by 2 minus 1. Let me just flip the reciprocal, so then we just get that this is the product of 2n plus 1 multiplied by 2n minus 1. And then we just divide this by 4n squared. But I can actually just combine these. So like just multiply both the binomials here. So we get that this is just, let's see, just rewrite the sigma of ln of, let's see, 2n. So this is like a difference of squares over here. So then this is 4n squared. Let's see, 2n minus 1, that's negative 2n, and then plus cancel. So this is just negative 1, and then divided by 4n squared. Actually, we can actually use the following rule that, let's see, yeah, over here should be good. Just write it. Well, I'll write this in black. We can use the rule that the sum of ln of a sub n is equal to ln of the product of a sub n, and that's just because it's continuous. So by continuity, so we can use this fact to convert this into a product series. So this means I can actually convert this into a product series. So the natural log of the product series, so from n is equal to 1 of 4n squared minus 1 divided by 4n squared. And now there's also one definition that we're going to use, and that's actually the everyone knows this as the Wallace product, which the Wallace product is defined as follow. It is defined as the same thing. So the product series from infinity to n is equal to 1 of 4n squared divided by 4n squared minus 1 is equal to pi over 2. Okay, so we can use that. However, because the numerators and denominators are in a different form, such as this, so really I can actually just flip its reciprocal. However, I can actually write it like this. So we know that this is equal to pi over 2. So rather to put this simply, why don't I just put it as so. So then this is, let's see, so this is negative ln of pi divided by 2. And rather that's equal to the negative product series of n is equal to 1 of 4n squared and then 4n squared minus 1. But if I just put the negative out here, then that means this is just ln of the product series of n is equal to 1 of 4n squared minus 1 divided by 4n squared. And simply that's just ln of its reciprocal, so it's 2 divided by pi. Okay, so we just use this. This is simply just pi, or ln of 2 divided by pi. Okay, cool. And I'll just underline that. And we're pretty much done. We have our series over here. So now just to write the conclusion, we have that, I'll write this in black. How about that? I'll write our final conclusion in black. So therefore, our integral from 0 to 1 of our fractional. So see, this is negative 1, and then the floor of 1 over x, and divided by x, fractional, so dx is just equal to 1 plus the natural log of 2 divided by pi. All right, cool. And there we have it. That's our that is our answer, like so, to find in this orange box. All right, that's pretty cool if you ask me.